If I told you that in the Tesla Model S Plaid's motor, steel is too soft, would you believe me? We usually think that to build a motor capable of outputting 1,000 horsepower, the casing must be made of the hardest steel to withstand that kind of explosive force. But in the extreme world of 20,000 revolutions per minute, the laws of physics change. Under this terrifying centrifugal force, a traditional high-strength steel sleeve actually behaves like a piece of flung-out clay. It expands and deforms, eventually crashing the motor directly. Steel simply cannot hold back this beast. So how did Musk solve this? He abandoned rigid steel and turned to something that looks like plastic and feels like fabric, carbon fiber. He used this soft material to forcefully bind this motor that was about to explode. Why can a few strands of carbon fiber do what steel could not? Today, we are going to deconstruct Tesla's counterintuitive black technology. First, we need to understand a fundamental physical problem. Why is it so hard to build a motor? If you want an electric car to go fast, as everyone knows, the core of an EV motor, especially a permanent magnet motor, is the thing in the middle that rotates, called the rotor. This rotor is covered with powerful magnets. When you step on the pedal, current enters the outer coils, creating a magnetic field that pushes these magnets in the middle. The rotor starts to spin frantically, driving the tires. Sounds simple, right? But under extreme conditions, things become very tricky. Imagine you are holding a rope with a brick tied to the other end. You start swinging it over your head. The faster you spin, the greater the force trying to make that brick fly away. This is centrifugal force. Now, scale this scenario up thousands of times. The Model S Plaid's motor spins at up to 20,000 revolutions per minute. At this speed, those magnets on the rotor endure thousands of times the acceleration of gravity g-force. Their desire to fly out is incredibly strong. If nothing binds them, the moment you hit the accelerator, this motor will turn into a hand grenade. Magnets will punch through the motor casing like shrapnel. So, before carbon fiber technology appeared, what did engineers do? Previous high-performance motors, such as early Teslas or other EV brands, would usually use a high-strength steel sleeve to wrap the magnets. It's like using a steel bucket to tightly hoop the magnets. This sounds reasonable. Steel is hard, right? But steel sleeves have 3 fatal physical flaws. This is why it's hard for traditional EVs to achieve insane top speeds like the Plaid. The first flaw, it's too heavy. Steel is a very heavy metal. Placing a thick layer of steel around the rotor is equivalent to increasing the rotor's rotational inertia. Simply put, the rotor becomes cumbersome. It reacts slowly when you want to accelerate, and it won't stop when you want to decelerate. For a car chasing 0-100 acceleration, every gram of weight is the enemy. The second flaw, and the most troublesome, thermal expansion. It is an iron law of physics. Metal expands when heated. When the motor is running at full speed, the temperature rises. At this time, that steel sleeve will start to grow larger and fatter. Combined with the centrifugal force from high-speed rotation, the steel sleeve will bulge outward slightly. What problem does this cause? A big one. The motor's rotor spins, while the outer stator remains stationary. A gap must be maintained between the two. We call it the air gap, because engineers know the steel sleeve expands when heated. To prevent it from rubbing against the casing and destroying the motor, they are forced to leave a very large air gap. The third flaw, eddy current loss. This is a bit more hardcore. Steel is a conductor. It is a metal. When you place a piece of metal in a strongly changing magnetic field, an induced current is generated within the metal. This is called an eddy current. This current is not only useless, it also generates heat. This means the steel sleeve itself becomes a heating element. This is a disaster because magnets hate heat. As temperature rises, magnets demagnetize, and the motor loses power. So to summarize the pain points of old technology, to bind the magnets, we use a steel sleeve. As a result, the steel sleeve is too heavy, expands, and generates heat, preventing motor efficiency and top speed from increasing. This is the wall that physics has given us. How did Tesla break through this wall? They thought of carbon fiber. Everyone's impression of carbon fiber might still be that it's just light and expensive. But for motor engineers, a counterintuitive property of carbon fiber is the real secret weapon. That is, it almost does not expand with heat. In fact, in certain directions, it even contracts when heated. This material was practically born for making motor rotors. Think about it, when the Plaid motor hits 20,000 revolutions per minute, and the temperature soars. If it were a steel sleeve, it would have already expanded and deformed. But carbon fiber, it remains as steady as a mountain. Even better due to its contraction property. The hotter it gets, the tighter it binds the magnets inside. It's like a straitjacket that tightens the more you struggle. What revolutionary changes does this bring? First, the air gap can be made incredibly small. Since I'm not afraid of the rotor expanding, I can set the gap between the rotor and stator to micron-level precision. Remember the fridge magnet analogy? Now we've removed the thick wooden board in the middle. The magnet sticks directly to the fridge. This drastically improves the efficiency of magnetic field transmission. This is why this motor is only the size of a handbag. One person can pick it up, yet it can unleash over 1,000 horsepower. This level of power density was previously unimaginable in engineering. Second, it solves the heat problem. Although carbon fiber contains carbon in this composite form, its conductivity is completely different from steel. It doesn't generate severe eddy current heating like a steel sleeve. This means the internal temperature of the motor is easier to control. Magnets can operate in a much cooler environment. This allows the Model S Plaid to perform multiple launch starts in a row without power degradation. Previous EVs might do 2 acceleration runs before the system throttles due to overheating. But here, that doesn't happen. Third, lightweighting. Carbon fiber is much lighter than steel. This keeps the rotor's inertia low. The moment you hit the pedal, the RPM shoots up instantly with zero lag. This is also why this large car feels as nimble as a small sports car. Now, you might think, wow, Tesla is a genius for inventing this technology. At this point, car enthusiasts or F1 fans might step in to correct me. Wait, this isn't a new technology. F1 cars have had this for a long time. Exactly. This technology was indeed not invented by Tesla. If you look at the engine structure of a Formula 1 car, there is a motor called the MGU-H motor generator unit heat. That thing is even more insane. Its speed isn't 20,000 revolutions per minute, but up to 125,000 revolutions per minute. At a terrifying speed of 120,000 revolutions per minute, steel really would be flung out like mud. So F1 was forced long ago to use carbon fiber winding technology to build rotors. So what makes Tesla impressive? If they're just copying F1's homework, what's there to brag about? The key lies into words mass production. You have to realize how F1 parts are made. It's top-tier technicians in white coats in a clean room, manually laying and winding layer by layer, then baking it in an autoclave. The cost of one F1 motor might be more expensive than the Mercedes parked downstairs, and its design life is only a few thousand kilometers. It's scrapped after a few races. But what did Tesla want to do? They wanted to take this aerospace-grade, racing-grade technology and stuff it into a mass-produced car that you can drive to buy groceries, with an 8-year warranty and hundreds of thousands of kilometers of range. And the cost had to be kept extremely low. That is the real engineering challenge. So, when we look at the Model S Plaid, we are not just seeing a fast car. We are seeing an engineering miracle, bringing high-end technology from F1 and centrifuges down to the civilian market. Finally, I want to ask everyone, how long do you think it will take traditional automakers to catch up with this mass-produced carbon fiber rotor process? Or will they choose a different path, such as adding more gearbox gears to solve the problem? Feel free to leave a comment below and let me know your thoughts. If you like this kind of hardcore tech teardown video, don't forget to like, subscribe, and hit the bell icon so you won't miss the next deep dive.